In this section, we'll talk about lightweight fine-tuning. In the last section, we talked about the pre-trained and fine-tuned paradigm, which is the key component for solving NLP problems nowadays. Given a pre-trained transformer model such as BERT, we can fine-tune that on many different downstream tasks, including text classification, sentence pair classification, sequence labeling, and so on. The downside, however, is that during fine-tuning, all parameters need to be updated, which is expensive, especially considering how large these models are. So an active line of research is to study how can we do efficient fine-tuning. And one line of work is focused on adapters. So the figure shows the process very clearly. Now, instead of fine-tuning the entire model, it would add an adapter layer or insert that layer into the model and then freeze the rest of the weights. Just train this adapter layer so that for each task, the only weights that's different from the pre-trained model are these adapters. And instead of copy the whole model for different tasks, we just need to take this adapter layer and share that instead. So here, if you consider the full model, that's more than 400 megabytes. But if we just use the adapter weights or adapter layers for different tasks, it's only about 3 megabytes. So this is the key idea in adapters. So an alternative of doing fine-tuning is in-context learning. Now, this only applies to left-to-right language models. So recall that in left-to-right language models, we try to predict the next word given the past sequence. So here, we can format the prediction task as a generation task. For example, in machine translation, the input is English phrase, output is the French phrase. And it doesn't necessarily have to be a sequence-to-sequence task. It could also be classification where the output is directly the label instead of a sentence. Now, the key point is that in context learning, we can directly put these examples in the prefix or the prompt and then predict the next token, which is the label for the last example. So this way, there is no fine-tuning per se, because at test time, we're not tuning the model parameters, but instead, we just put the examples in the prompt and using the language model to directly predict the output. So here, even though there's no fine-tuning, an important variable is what examples do you put in the prompt, because that can have important effect on the model's performance. And I just want to quickly mention one line of work using prompt tuning. Here, the idea is that instead of selecting discrete prompts from existing examples, we would directly learn a good prompt. So now this prompt or the embedding of the prompt is still computed from a small amount of parameters, but the point is that it's much cheaper than tuning the entire language model. The overall idea here is similar to the adapter layer. In both cases, instead of tuning the large model, we just tune a small part that's inserted or attached to the large model to save computation.